In the 1930s, telecommunications relied on massive mechanical switchboards. To route a single telephone call, current had to pass through sprawling banks of clicking relays and thousands of hand-soldered copper wires. Designing these circuits was an intuition-based art form. Engineers drafted complex electrical paths based on experience and rules of thumb, as there was no rigorous mathematical system to determine if a design was actually efficient. When an engineer wanted to simplify, they were forced into a 21-year-old student at the Massachusetts Institute of Technology named Claude Shannon proposed a mathematical solution to these design limitations. Shannon submitted a thesis that historians and colleagues would later characterize as the most significant master's thesis of the 20th century. His work demonstrated that the abstract Boolean algebra of the 19th century was mathematically identical to the behavior of physical electrical circuits. By treating copper wires as logical variables, Shannon provided the framework to move circuit design from a manual craft to a predictable mathematical discipline. This schematic shows an electromechanical relay. When voltage hits the coil, a magnetic field closes the circuit. Shannon mapped these physical states to binary values, a closed circuit representing a 1 and an open circuit representing a 0. Shannon worked with existing technologies. He did not invent the relay or binary numbers. Instead, he developed the mathematical translation layer required to connect the two. He repurposed the logic of George Boole, which was originally used in philosophy to evaluate whether statements were true or false, and applied it to the physical on-off states of electricity. By representing hardware as logic, Shannon allowed engineers to calculate the behavior of a circuit before any physical construction began. In his 1938 paper, Shannon defines his first postulate with two switches, X and Y, in series. Current only flows if switch X and switch Y are both closed. This series connection physically represents a logical AND gate, or algebraic multiplication. Figure 2 shows the second postulate, a parallel circuit. The path splits. Current reaches the destination if switch X or switch Y is closed. This parallel connection is the physical equivalent of a logical OR gate, or algebraic addition. Shannon also defined negation, using a prime symbol to represent a relay that breaks the circuit when it is activated. This acts as a logical NOT gate. With AND, OR, and NOT defined in hardware, the focus of circuit design moved from physical manipulation to algebraic calculation. Figure 5 shows an unoptimized circuit. We mathematically describe the path from terminal A to B. Starting at A, the path through relay W splits into parallel branches, adding a plus sign. The middle branch contains W' in series with parallel X and Y. By continuing this process for every connection, we can translate the entire physical network into a single algebraic equation. This is the raw equation for the circuit we just saw. We can now solve for the simplest version of this circuit using pure mathematics. We start by applying Shannon's theorem 17b to the first section. The W' term is redundant, so the section reduces to just W plus X plus Y. Next, we use the distributive law to multiply the complex terms together. This expansion produces a long string of variables representing every possible logical state of the circuit's branches. We then look for contradictions. A variable multiplied by its own negation, like z times z prime, equals 0. Because a switch cannot be open and closed simultaneously, these terms are removed. After factoring the remaining variables, we are left with a final reduced equation, w plus x plus y plus z s prime v. By simplifying the math on paper, Shannon showed how to remove physical relays from the design without changing its function. Now we translate the math back into hardware. W, X, and Y are placed in parallel, while Z, S prime, and V are wired in a single series line. This is the result. Figure 5 is the original circuit, requiring roughly 14 components. Figure 6 is Shannon's optimized version, performing the exact same task using only 6. While these reductions saved space and money, Shannon used the final pages of his thesis to reach a much larger conclusion. He realized that if switches process logic, they can also process arithmetic. In figures 35 and 36, he describes an electric adder. This arrangement of switches allows the hardware to add binary numbers and automatically carry the remainder to the next position. This logic is the basis for the arithmetic logic unit found in modern processors. Shannon had demonstrated that any logical or mathematical operation could be executed using a specific arrangement of switches. Shannon's thesis provided the first formal link between abstract symbolic logic and electrical engineering. This mathematical framework replaced the trial and error methods of the early 20th century, allowing digital circuit design to become a rigorous science. As the hardware evolved from mechanical relays to vacuum tubes and eventually to silicon transistors, the design process remained the same. The mathematical principles Shannon outlined in 1937 continue to govern how modern systems process information at the atomic scale. Every operation currently occurring inside your computer or phone is an execution of these exact postulates. After establishing the logic of circuits, Shannon turned his attention to the nature of communication itself, leading to his 1948 work on information theory. To see our deep dive into that next breakthrough, like and subscribe to the channel. Exploring these original foundations is the best way to understand the technology we use every day.